So we've just looked at polar form of complex numbers. We looked at the operation of multiplying and dividing complex numbers in polar form and an exponential form. So let me go through a couple more examples and then show you de Moivre's theorem and how to find the nth root of a complex number. And so recall we looked at the polar form of a complex number. Our value r was greater than or equal to 0. Our theta value was between 0 and 2 pi. And we saw that the complex number x plus I y can be written in polar form as r cosine theta plus r sine theta times I, or we can factor out that r value and we get r times the quantity cosine theta plus I sine theta. We saw that Euler's formula helped us rewrite a complex number in polar form and exponential form. The theorem of Euler's formula is that e raised to the I theta is equal to cosine theta plus I sine theta. So Euler's formula allows us to write the polar form of a complex number using exponential notation. So this r times the quantity cosine theta I sine theta is equal to r times e to the I theta. So when a complex number is written in the form of z equals r e to the I theta, it's said to be written in exponential form. So we looked at the property of multiplying and dividing complex numbers. If it's in exponential form of the complex number, z sub 1 defined as equal to r sub 1 times e to the I theta sub 1 power. And we defined z sub 2 equal to r sub 2 e raised to the I theta sub 2 power. Then if we multiply our two complex numbers, z sub 1 times z sub 2, we see that that's the same thing as r sub 1 times r sub 2, e raised to the I times the quantity theta sub 1 plus theta sub 2. In polar form, we saw that this was the same thing as z sub 1 times z sub 2. This was equal to the product r sub 1, r sub 2 times cosine of the sum of our two angles, theta sub 1 plus theta sub 2, plus I times sine of the sum of our two angles, theta sub 1 plus theta sub 2. If we were dividing two complex numbers, z sub 1 divided by z sub 2, we could write it in exponential form of the complex number by looking at the quotient r sub 1 and r sub 2, so r sub 1 divided by r sub 2 times e raised to the power I times the quantity theta sub 1 minus theta sub 2. In polar form, z sub 1 divided by z sub 2, this is equal to r sub 1 divided by r sub 2 cosine of the difference of our angles, so theta sub 1 minus theta sub 2, plus I sine of theta sub 1 minus theta sub 2. So let's look at an example of multiplying and dividing two complex numbers. So the example says we're going to look at finding z times w and z divided by w. We want to write each answer in polar form, exponential form, and in rectangular form. So we're given that z is equal to 2 plus 2i, and we're given that w is equal to the square root of 3 minus I. So it's going to be much easier if I first convert these into polar form or exponential form, and then work with the rules of multiplying and dividing our complex numbers. So let's convert this into polar form. So recall, r is equal to the square root of my real part, x quantity squared, plus my imaginary part, which is y quantity squared. And we can find theta by looking at the tangent inverse of my imaginary part all over my real part. So let's first look at z and let's plot z. So on the rectangular coordinate system, the imaginary is our vertical axis and our real part is the horizontal axis. So plotting 2 plus 2i, I would go over 2 to the right and up 2. So let's form our rectangle. And so I know that the height there is 2, my base there is 2. And I can find r. I know that r here is equal to the square root of my real part, which is 2 quantity squared, plus my imaginary part, which is 2 quantity squared. So r is equal to the square root of 4 plus 4, or r is equal to the square root of 8. So pulling out the factor that is a perfect square, I can rewrite 8 as 4 times 2. And so r is equal to square root of 4, which is 2. And then we're left with root 2. So r is 2 root 2. I need to figure out what theta is. So looking at my triangle, the values that were given to us are the opposite and adjacent. And again, we know that tangent deals with opposite and adjacent. So theta is equal to tangent inverse of my y value, which is the opposite 2, over my adjacent value, which is x, which is 2. So theta is equal to the tangent inverse of 1. So the angle that gives me back tangent of the angle that gives me back 1, I know is pi fourths. So theta is equal to pi fourths. So now I can write my value of z in polar form. In polar form, I have my r 2 root 2 all times cosine of my angle, which is pi fourths, plus I sine of my angle, which is pi fourths. So this is z in polar form. I want to do the same thing for w. So let's look at w. W, I can figure out what r is. R is equal to the square root of my real part, which is root 3 quantity squared, plus my imaginary part. My imaginary part there is -1, so -1 quantity squared. So r is equal to the square root of 3 squared is 3, -1 squared is 1. So I get that r sub w is equal to the square root of 4, which is equal to 2. So I'm going to define these as r sub z, theta sub z, just to be cognitive of which one is which. So if I plot this w on the Cartesian plane, I would go over to the right, root 3. But my imaginary part is negative, so I'm going to go down 1. So I'm in here in the 4th quadrant. So we need to be careful when we're looking at our value of theta and know that we're in quadrant 4. And so we have what our R value is, we saw was 2. So I'm looking at my reference angle here. I'm going to call it theta sub r for reference angle. So I know that theta sub r, my reference angle of my triangle, is tangent of adjacent, which is my 1, all over my, opposite, which is 1, over my adjacent, which is root 3. So theta sub r here is equal to tangent, rationalizing inverse. Rationalizing my denominator, I know I get root 3 over 3. So my reference angle there in the 4th quadrant for theta is going to be 30 degrees, which is pi 6. So theta for my W value, I'm in that 4th quadrant. So I know my reference angle is pi 6. So 2 pi minus pi 6 would give me 11 pi 6. So now I have the information. And let me rewrite W in polar form. So W here in polar form is equal to R, which is 2, times the quantity of cosine of my angle, 11 pi 6, plus I sine of 11 pi 6. So now when I'm looking at Z times W, I know that this is equal to my R value for Z times my R value for W. So I have my R value for Z is 2 root 2 times my R value for W, which is 2, all times cosine. I'm summing my values for my angles, which is pi force plus 11 pi 6 plus I sine, again, the sum of my angles, which are pi force plus 11 pi 6. So let's clean this up a little bit. I have Z times W is equal to, so if I multiply 2 root 2 times 2, this is the same thing as 4 root 2. Cosine. To add these angles together, I need a common denominator, and my common denominator of 4 and 6 would be 12. So to get a common denominator of 12 for pi force, I would multiply by my fancy one of 3 over 3. And to get the common denominator of 12 for 11 pi 6, I would multiply this by 2 over 2. So I have 3 pi 12ths plus 22 pi 12ths. So 3 pi plus 22 pi, that is 25 pi over 12. Plus I sine, I already did the work for the other one, which is 25 pi 12ths. So here it is, the product of those two complex numbers in polar form. To rewrite this in exponential form, Z times W is this 4 root 2 EI to that sum of those two angles, which we found to be 25 pi over 12. So we can go back and we can evaluate this, and we can get a estimate of what this would be in rectangular form. So I have 4 root 2 I need to evaluate what cosine of 25 pi over 12 is, and I need to evaluate what sine of 25 pi over 12 is. So when I plug this into the calculator, I want to make sure that I have this in radians. Okay, so plugging that into my calculator, cosine of 25 pi 12ths I get is approximately 0.96 or 97 plus I, plugging in sine of 5 pi 12ths into my calculator, I get approximately 1.46. So now if I distribute this 4 root 2 to both of those terms inside the parentheses, I get back that my real part is approximately 5.46 plus my imaginary part, which is 1.46 times I. So right there, that is the multiplication of Z times W. So we now want to look at the quotient of Z and W. So Z divided by W, well, we did a lot of the work right now because we've already converted these into polar form. And so to look at Z divided by W, this is equal to Z, or R sub Z, which we saw was 2 root 2, divided by our R sub W. R for our complex number W we found was, there we go, 2, all times cosine of the difference of our two angles. So our angles were pi fourths minus the angle, which was 11 pi 6, plus I sine of the difference pi fourths minus 11 pi 6. So let's simplify this a little bit. 2 root 2 divided by 2, the 2's cancel, leaving us with root 2. Cosine, again, we need to get a common denominator. We saw that we had 12 as the common denominator, so 3 pi 12ths minus 22 pi 12ths. So 3 minus 22 gives us negative 19 pi 12ths. Plus I sine of negative 19 pi 12ths. So let's use the fact that cosine is an even function. So cosine of a negative angle is the same thing as cosine of that angle. So this gives us back root 2 cosine of 19 pi 12ths. And sine is an odd function. So sine of negative theta is the same thing as negative sine of theta. And so we can say that I sine of negative 19 pi 12ths is negative I sine of 19 pi 12ths. So here is the polar form of Z divided by W. And so our exponential form is going to be root 2 e to the I theta. And theta we saw was 19 pi over 12. So let's look at a couple more rules and a couple more examples. the argument of a complex number is periodic. So that says that r to the I theta, this is equal to r to the I times the quantity theta plus 2 k pi, where k is an integer. So we have de Moivre's theorem in front of us. De Moivre's theorem states that if z is equal to ri theta is a complex number, then if I raise z to the nth power, this is equal to r raised to the nth power all times e I to the n theta, where n is greater than or equal to 1 is an integer. In polar form, de Moivre's theorem says that z raised to the nth power is equal to r raised to the nth power of the quantity cosine of n times theta plus I sine of n times theta. Again, n is greater than or equal to 1. So knowing de Moivre's theorem, let's look at raising a complex number in rectangular form. Actually, this was in rectangular form. This is in polar form. And rewriting it in rectangular and polar form, an exponential form. So the next example in front of us states that we have a complex number, √3 times cosine of pi 18ths plus I sine of pi 18ths. And that whole quantity and everything I just stated is raised to the 6th power. So knowing that, let's rewrite this using de Moivre's theorem in polar form. So this says that I can take my r value, and my r value here is √3. So I'm going to write √3, and I'm going to raise this to the 6th power, all times cosine of n is 6 here, times my angle of pi over 18, plus I sine of n, which is 6 in our case, times pi over 18. So let's simplify this a little bit. I noticed that 6 goes into itself once and 18 3 times. Also, I'm going to use the rule of exponents. So a rational function, the square root of 3, this is the same thing as 3 raised to the 1/2 power. And I know power to power. So if I have √3 raised to the 6th power, I can rewrite this in exponential form, 3 raised to the 1/2 power, and raising that to the 6th power. Power to power is multiplication. So this is 3 all times 6, or all raised to the 6 times 1/2 power, which gives me 3 cubed, and 3 cubed is 27. So I have here √3 raised to the 6th power is 27, all times cosine. My angle is now, or argument is now pi thirds, plus I sine of pi thirds. So this right here is my polar form of that complex number in polar form raised to that 6th power. In exponential form, I would have 27 e raised to the I times my argument, which is pi thirds. If I want to write this in rectangular form, so let's go back to the polar form right here, and let's simplify it. So I have 27 times the quantity of cosine of pi thirds. So cosine of pi thirds is 1/2 plus I sine of pi thirds. Sine of pi thirds is √3/2. So this is equal to, let's distribute our 27. I have 27/2 is my real part, plus I, 27 times √3, so 27√3, all over 2. So here's my rectangular form of my answer. Now let's look at another theorem, and it's based off of de Moivre's theorem. If we wanted to look at a nth root of a complex number. So in front of us, I have a theorem for finding the complex roots. So suppose that W is equal to R raised to the I theta is a complex number and n is greater than or equal to 2 is an integer. If W does not equal 0, there are indistinct complex roots of W given by the formula Z sub k is equal to the nth root of R, and that nth root of R is all times e raised to the I times 1/n times the quantity theta plus 2 k pi, where k is defined to be 0, 1, 2, ... up to n minus 1. So writing that in polar form, so what I just gave you was exponential form. If I'm looking at the nth root of z, this is equal to the nth root of my value r, all times cosine of theta plus 2k times pi divided by n plus I sine of theta plus 2k pi all divided by n. Where again, k are the numbers 0, 1, 2, ... to n minus 1. So let's look at a couple examples of finding the nth root of a complex number. So we're given that we want to find the fourth root of -16i. So find the complex roots, write your answer in polar and exponential form. So I'm given the complex number -16i, and I want to find the fourth root of -16i. Well, let's first look at -16i. So really my real part here is 0, and my imaginary part here is -16. And so if I plot this point, well, I'm not going left or right because my real part is the horizontal axis. I'm going down 16 because my vertical axis is my imaginary axis. So my point is lying here on that vertical axis. And so if I think about this, let's figure out what r is. Recall r is equal to the square root of my real part squared, so 0 squared, plus my imaginary part squared, so -16 quantity squared. So r is equal to the square root. Well, if I square -16, that's the same thing. So -1 times -1 is 16 quantity squared. And so r is equal to 16. If I look at my angle theta, theta here is 3 pi halves. So in the complex form, this is equal to r, the fourth root of r, which is 16, all times cosine of theta, 3 pi halves, plus 2 pi k, all divided by n, and we're looking at the fourth root, so all divided by 4, plus I sine of the same thing. So let me move this stuff over. And so, just like we had before, 3 pi halves plus 2 pi k all over n, which was 4. So I need to look at k. K is equal to, start at 0. I do start at 0. So 0, 1, 2, and to n minus 1. So 4 minus 1 is 3. So to 3. So I'm going to have 4 different roots here. So I have the fourth root of 16. Well, 16, can we take the fourth root of 16? Well, 16 is right 2 to the fourth power. So the fourth root of 16 is just 2. All times cosine. Let's start with k equal to 0 first. So if I have k is equal to 0, that 2 pi times 0 is going to go away. And I'll have 3 pi halves divided by 4. So let's just look at that really quickly. So 3 pi halves divided by 4. So this is 3 pi halves times the reciprocal of 4, which is 1/4. So this gives me 3 pi eighths. Plus I sine of 3 pi eighths. If I let k equal 1, then I would get that my answer is equal to 2 cosine of 3 pi halves plus 2 pi times 1 is 2 pi all over 4. Plus I sine 3 pi halves plus 2 pi all over 4. So that 3 pi halves plus 2 pi, I need a common denominator. So my common denominator is 2. So that 2 pi, I can multiply by 2 over 2. And so I have really 3 pi halves plus 4 pi halves all over 4. So that gives me 7 pi halves. Doing some work on the side. Times the reciprocal of 4, which is 1/4. So this gives me 7 pi eighths. So this is equal to 2 cosine of 7 pi eighths plus I sine of 7 pi eighths. So we have so far 2 of our roots. Now let's look at k is equal to 2. So plugging in 2 for k here. This is equal to 2 cosine of 3 pi halves. Well, 2 pi times k, which is 2, is 4 pi. All over 4 plus I sine of this 3 pi halves plus 4 pi all over 4. So doing some work on the side, we have this 3 pi halves plus 4 pi, but I need a common denominator. So 4 pi is the same thing as 8 pi over 2 divided by 4. So my numerator, 3 pi halves plus 8 pi halves, this is 11 pi halves. Divided by 4 is the same thing as multiplying by the reciprocal of 1/4, which gets me 11 pi eighths. So when k is 2, I have 2 times cosine of 11 pi eighths plus I sine of 11 pi eighths. So one more I need to do. I need to look at when k is equal to 3. So some more room. So k is equal to 3. So when k is 3, I get 2 all times cosine of 3 pi halves plus 2 pi times k, which is 3. 2 pi times 3 is 6 pi. Let's get a common denominator right now. So 6 pi with a common denominator of 2 is 12 pi halves all over 4 plus I sine. Well, 3 pi halves plus 12 pi halves is 15 pi halves. 15 pi halves times the reciprocal of 4. So 15 pi halves. Let's just write it. Times the reciprocal of 4, which is 1/4. So simplifying that, we get this is 2 times cosine of 15 pi eighths plus I sine of 15 pi eighths. So let's put this now in exponential form. So exponential form here is 2e raised to the I times 3 pi eighths, or 2e raised to the I times 7 pi eighths, or 2e raised to the I times 11 pi eighths, And the last one gives us back 2e raised to the I of 15 pi eighths. So we found the fourth root of negative 16i, and we put them in polar form and exponential form. If we wanted to evaluate this and put this in rectangular forms, then we would look at plugging these values into our calculator, cosine of 3 pi eighths, and then looking at sine of 3 pi eighths, and multiplying that by our R value in front, where I is in front of the sine. Okay, so looking at one more example, where we're putting our answer in both polar form and exponential form. So our next example here, we're given, we want to find the cubed root of negative 8 minus 8i. So let's first look at z equals negative 8 minus 8i. And let's first put this in polar form. And so let's plot that first. So my real part is negative 8. So I'm going to go over 8 on the horizontal axis to the left. And I'm going to go down 8 on my imaginary axis. And so I'm in my third quadrant here. I can make my triangle. I can figure out what R is. R is equal to the square root of my real part, which is 8, negative 8, quantity squared, plus my imaginary part, which is negative 8, quantity squared. So R is equal to the square root of 64 plus 64. So R is equal to the square root of 128. So I'm looking to see if there's any factors of 128 that are perfect squares, and I'm looking for the biggest one. So if I don't know it, then rewriting it sometimes as a product of prime factors is helpful. I know that 4 goes in 128. I know 4 is a perfect square, but 4 goes into 128 32 times. I know 16 is a factor of 32, and 16 times 2 is 32. So looking at this, I'm combining my two perfect squares, 4 times 16, which is 64. So R is the same thing as the square root of 64 times 2. So R is equal to, taking the square root of 64, I get 8, and then I'm left with root 2. So I figured out what my R value is. I'm wondering if maybe actually keeping this, let's keep this without pulling out the factor. I forgot that we have to look at the root of that, and that might be easier if we just kept it as right now. R is equal to the square root of 128. I know that that's the same thing as 128 raised to the 1/2 power. I need to figure out what theta is. Let's look at this as our reference angle first. So my reference angle, theta sub r. So this is equal to tangent inverse of the opposite, which was negative 8, all over the adjacent, which is negative 8. I have my reference angle, tangent inverse of 1. So I know that my reference angle here is pi fourths, but I'm in the third quadrant. So theta is going to equal pi plus pi fourths. So common denominator, I have 4 pi fourths plus 1 pi fourths, which is 5 pi fourths. So in polar form, my z value is equal to r, which we said was the square root of 128, all times cosine of theta, which is 5 pi fourths, plus I sine of 5 pi fourths. So if I want the cubed root of z, so the cubed root of z, this is by my formula, is the square root of 128. That is taking the cubed root of that. All times cosine of my angle 5 pi fourths plus 2 pi k, all divided by what root I'm taking, which is 3, plus I sine of, let's get a common denominator right now, and let's simplify this a little bit easier. So when we plug in k, it's a lot easier to do. So my common denominator of 5 pi fourths and 2 pi k is 4. And so multiplying 2 pi k by 4 over 4, that's 8 pi k. So this is the same thing as 5 pi plus 8 pi k all over 4 divided by 3. So the square root of 128, it can be rewritten as 128 to the 1/2 power, all raised to the 1/3 power, which is the same thing as the cubed root of times cosine of, let's multiply that 5 pi times or plus 8 pi k over 4 times the reciprocal 3, which is 1/3. So that would give me 5 pi plus 8 pi k all over 12 plus I sine of 5 pi plus 8 pi k all over 12. I'm trying to find the cubed root. So I know, again, my n value was 3. And so I need to look at when k is equal to 0, 1, and 2. Recall power to power is multiplication. So I'm looking at 128 to the 1/6 power of cosine. So let's look at first k equals 0. So if k is equal to 0 here, that would be 5 pi over 12. Cosine of 5 pi over 12. Plus I sine of 5 pi 12ths. Let's just see if we can simplify 128. What did we just say that was? 128, we said was the same thing as 64 times 2. I'm looking at the 6th root. I need something that, so 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 64, times 2 is 128. So noticing that the 6th root of 128 is the same thing as the 6th root of 2 to the 6th power, which would equal 2. So right here, this 6th root of 128, I'm going to rewrite in simplified form as 2. Now I need to look at when k is equal to 1. So plugging in 1 for k, this would equal 2 all times cosine. Well, k is 1, so 8 pi times 1 is 8 pi, plus that 5 pi is 13 pi all over my 12, plus I sine of 13 pi all over 12. One more, we need to look at when k is equal to 2. So if k is equal to 2, I have 2 times 8 pi is 16 pi. 16 pi plus 5 pi is 21 pi. So we would have here, this is equal to 2 cosine, what did I just say, 16, 21 pi 12ths plus I sine of 21 pi 12ths. So there are 3 roots written in polar form and in exponential form. This would be 2e to the raised to the I 5 pi 12ths, or 2e raised to the I times the 13 pi 12ths, or 2 times e raised to the I, and the I is times 21 pi 12ths. And just notice that 21 pi and 12 have something in common, so we could technically reduce that fraction. So that would be 2 cosine. They both have 3 in common. 3 goes into 21 7 times, so 7 pi. 3 goes into 12 4 times, so 7 pi 4ths plus I sine of 7 pi 4ths. So in that form, that is equal to, for exponential, 2 times I raised to the 7 pi over 4. So we have our 3 roots of that -8 minus 8i. That was in rectangular form and polar form. And in exponential form. So for our class, that is the rest of section 10.3 in our textbook.